Chairman. Good morning, everybody. First thing I would like to express is my thanks to the organizing committee to invite me. I'm very honored to be asked to give a presentation here. And my special thanks go to, of course, Tatjana, who organized everything so well that everything ran smoothly. Very good, very good. Perfect. My talk is entitled Simulation. Sorry. Yes. Acoustics. Can you hear me? Yeah, very good. No, you cannot hear me. Now you can hear me. Yeah, that's very good. Yeah, my talk is entitled Simulation of Aircraft Installation Noise, a Key to Low Noise Aircraft Design. The subtitle is really pointing a little bit into the future, but what I really think is that installation noise is something of very much relevance and maybe overlooked a little bit, and that's why I'm focusing a little bit on this topic in this talk. The outline of this presentation is as follows. I will give a short introduction why I think that installation noise is very important. Then talk about two categories of installation noise: installation sources of noise and acoustic installation effects. Then I will try to draw some conclusions concerning what that means for aircraft noise reduction in general. And finally, I will maybe have some thoughts about a low noise impact aircraft, how that could be made. What you all know, of course, is the various sources of noise which are shown usually for aircraft. And the typical thing of this is you have components, single components, which generate noise. And the concept and thinking behind this is that the overall noise of the aircraft is basically the addition of all the superposition of all these component sources. May they be engine component sources like the jet noise, the fan noise, for example, or airframe noise, more important in the approach phase of the aircraft. Where you have high lift noise, a landing gear noise, and the noise of little engineering details on such an aircraft. So this is standard knowledge, so to speak. I don't want to go into any details of this, but rather focus on a different issue of noise on aircraft, and that's installation-related noise at aircraft. And the first thing I would like to give some sort of a definition, what I mean when I talk about installation sources. These are sources of noise on an aircraft which are generated due to the aerodynamic interference between several aircraft components. Those aircraft components do not necessarily have to be themselves sources of noise, but the interaction, the aerodynamic interference of these components make a new source of noise. The other category is acoustic installation effect, and what I mean by this is when you have a component which is subject or near the aircraft surface, of course will change radically the radiation of these component sources. Both things I think are very important, and that's basically the outline. I would like to start with installation sources and show you some examples. This is again the same picture, but now I only listed the installation sources which are on an aircraft, additionally to what we saw before. There's a whole bunch of them, and I would like to focus on some of them. The first thing I would like to mention is landing gear noise is very important for both for short, medium-range aircraft as well as for long-range aircraft. But it's not the landing gear itself alone which is important, but the interference of the landing gear wake with the high lift system is another source of noise, and I would like to show you a little detail on that. Quite a long time ago, we did some flyover tests on an A319 together with Lufthansa. That's quite some time ago. We looked into this data recently, to look at this issue. You see here now 3 diagrams. Please maybe only look on the left-hand side diagram first. What we did is we looked at the contribution of the high lift systems when they are extended fully, and the landing gear is up. It's not down, but it's up. So it's only the noise of the high lift systems which we measured in a flyover position. This is a certain flyover position of the microphone. The other situation is you extend the high lift system full, and additionally you put the landing gears down. Then what you observe is the red curve. It is much higher in level than, of course, only the high lift system extended by itself. So the question is the red curve basically the addition of high lift noise plus landing gear noise? And this is not the case, which you can see on this graph, on the green graph. What we did there is we did also a test where we had the high lift system up, so not extended, clean wing, and the landing gear down, meaning that the landing gear was not subject to the high lift flow around the extended flaps and so on. Then, of course, you have to fly faster, and you don't have the circulation effect of the high lift system on the local flow of the landing gear. But you can correct for that using a U to the power 6 law. And then you can really add the high lift noise separately plus the landing gear noise separately. And when you do that, you end up with a green curve, meaning the whole thing is more than the addition of the 2 sources, meaning there is an extra source acting, which is about 2 decibels in addition to the simple addition of the 2 sources, and it's relevant in the maximum of the sound radiation. So it's indeed relevant. We did also some time ago a related test in our small acoustic wind tunnel in Braunschweig, where we had a model scale landing gear leg and a high lift system attached, so the wake of the landing gear would hit the flap. And what you saw with source localization was definitely an extra source right at the leading edge of the flap, not the trailing edge, but the leading edge of the flap, which also indicates there is another source. Okay, there are ways to reduce this, but I don't want to focus on that too much. That is one important installation effect. And think of it, if you reduce the noise of your landing gear by putting on noise reduction technology on the landing gear, and you can make this landing gear completely silent, you would still have a source which is a bit more than the whole landing gear source is only reduced by 2 dB or so, because the landing gear flap interaction noise is still there. So it's really important. Another important effect is also a positive installation effect, the fact that the high lift wing is generating a lot of circulation, and the circulation, of course, reduces the local flow speed seen by the landing gear, which you can simply model with a simple model. For example, if you look at the flow field of a high lift system, you see, of course, that the local flow speed below this high lift system reduces the local flow speed, and if you place a landing gear here, it sees a locally reduced flow speed. You can model that very easily analytically with potential flow. And in order to compute the velocity deficit, you can do that very simply and compare that with the CFD solution. And the dashed curve is the simple analytical formula, and the solid curve is the taken from the CFD. What you see here is how the local flow speed reduces with the distance from the high lift system. And when you are, say, about one length of the landing gear leg away, you have a reduction of already 80% to 80% of the flight speed. And that translates into significant effects on the landing gear noise, because it scales with the 6th power of the local flow speed, and so you can achieve easily reductions of 3 to 4 dB. So it is good to have a landing gear very close to the wing. Long leg landing gears are very bad. Okay, that is a positive installation effect. Another installation effect, which is of course very important, is the propulsion system. And I would like to show you now an example of a counter-rotating prop fan. We did some simulations based on U-runs on counter-rotating prop fan in installed conditions where you have a pylon in front of it. And we subtracted the same case without pylon, and then you can isolate the installation effect, which is behind this pylon installation for a takeoff configuration here. Here we plotted only the additional noise you get due to installation, and this additional noise may amount to something like 6.5 decibel extra noise just due to the installation of the pylon. It is quite interesting, I don't show that here, but what we also saw is that in high speed you have sometimes a reversal of this effect. You may have reduction of radiated noise due to a pylon. It's quite interesting to see that. But for low speed, like typical takeoff situation or landing situation, any installation typically increases the noise. The other thing I would like to show is an experiment and also computations we did in our local wind tunnel in Braunschweig. We have 2 acoustic wind tunnels in Braunschweig DLR. This is the larger one. It's a 3 by 3 meter facility where we had an installed propeller in relation to a high-lift wing. High-lift wing was a special high-lift wing. It is a circulation-controlled high-lift wing, so an actuated high-lift system. And our task was to look at the sound radiation of this installed propeller. We saw with a microphone array that we see sources not only on the propeller but on the leading edge of the wing and on the trailing edge of the wing. This was propeller noise, so it was tonal. And what we saw is basically this. We did a simulation of this case, but before we did a very simplified simulation with three forces, rotating forces. So these rotating forces generate tip vortices, which then get convected downstream. And if you plot the pressure field, you see that in the rotation plane where those sources rotate, you see the typical spiraling pattern of propeller noise. And behind you see these vortices developing downstream. As you put into, and they are silent, of course. This vorticity is silent because it's just convecting. As soon as you put a plate or something inside this vortex system, you get, of course, a new source of noise there, which is very similar to what the helicopter people call blade vortex interaction noise. But you have that in an installed propeller too. So then we went with our simulation, CAA simulation, to this actual case here. You see here one result of the 3D simulation of this high-lifted wing. You see here the propeller plane, and you see the spiraling wave fronts from the propeller in the propeller plane. But if you look at the other planes here, especially the ground plane where the wing was installed, you see systems of other sound sources, systems of other waves. And one wave is this: when you draw these lines of these wave patterns and trace back where they come from. Sorry, that is the wrong one. I have to start with first. Yeah. Then you see that you find the source at the leading edge of that wing. And if you there's another wave pattern where when you trace it back to the origin, you find the knee of the flap. The reason is that vorticity, which comes from the propeller tip vortices, hits the airfoil and is strongly accelerated near the knee of this flap. So propeller noise, tonal propeller noise, is not only on the propeller, it's also generated on the wing behind the propeller. We could also validate this result. So we got a strong installation effect on the noise radiation of that propeller, and we were really able to validate our simulation with experiment. That was, by the way, the CA simulation was linear Euler simulation, linearized Euler simulation over Rahn's background flow. Okay, so this is another installation effect. Yet another installation effect related to the propulsion system is a jet flap interference noise. And let me show you one example out of this. We did a test in our wind tunnel in AWB in DLR with this F-16 high lift system with a droop nose. And we had a single stream, very simplified single stream jet to simulate, so to speak, a jet flow. We had microphones laid out below that system, with microphones upstream and downstream of the system, and we observed the following. If you see the spectra which you measure, you can look in blue. This is the spectrum you have if there was no jet. That's flap noise alone, flap noise, isolated flap noise. If you then measure jet noise separately and flap noise separately and add those two contributions energetically, you get the red curve. And then you can also measure the whole thing as is, and you basically get the same. So in this case, the whole thing is the addition of two sources. That's easy. If you look upstream, the story really changes, because then same thought as before, and the total noise is not the addition of the two sources, flap noise and jet noise. So there must be an extra source in the upstream direction. And we did a little CAA simulation for this case also. You see the jet hitting this flap, and you definitely see a wave pattern related to this the orientation of the flap. This clearly shows a typical trailing edge noise pattern, which does not radiate in the downstream direction, as trailing edge noise does not radiate in this direction. So you cannot see this extra effect in this downstream direction. But if you look upstream, you have this extra contribution, and you see the noise increase. That was our first simulation in this area. And recently we did a much more involved simulation in an EU project called Geronimo, where tests were made in the lab of Peter Jordan in Poitiers on a single stream jet in relation to NACA 0012 airfoil without any angle of attack. And here you see also definitely you see a noise radiation, anti-phase noise radiation related to the airfoil, and you see of course jet noise too. The measurements were those symbols here in the spectrum, and our simulation, later on I'll tell you something about the simulation, are the solid lines which show very nicely exactly the effects we see. We see on these microphone position above and below the airfoil in the same distance, we see a very strong increase of noise in the low frequency part. While when you look in the spanwise direction, where you cannot expect any effect of an airfoil because the airfoil does not radiate in the spanwise direction, you would expect something like a standard jet noise pattern, and that's exactly what you see in the measurements here in the black curve. Now the interesting thing is that also you have not only this extra noise due to the installation of the airfoil, but you have also acoustic shielding. So there is an extra effect due to the fact that especially high frequency noise of the jet is for this microphone here is partially shielded by the airfoil, while this is not the case on the lower microphone. That's why you see in the high frequency that on the red microphone you have basically no effect, but for the blue microphone you have a noise decrease due to acoustic shielding, basically. This is in a way a little bit of an academic case, because the flow of the jet is not at all influenced by the airfoil. So it's very symmetric and forms coherent structures, large-scale coherent structures, which generate these low-frequency components. The simulation was based on a new approach we are developing at the moment, which we call forced eddy simulation. It's not LES. It is based on a stochastic forcing on the non-resolved scales. So the concept is to have always a RAND simulation of the background flow, and then do a nonlinear perturbation analysis over this RAND's background flow. We use for the excitation of the sound field, we use a stochastic model, a stochastic four-dimensional turbulence realization, so to speak, and we bring it in through a relaxation term in the momentum equations. What we actually do with this approach, we set up a so-called backscattering model. That means that we can use very large grids, grids with very big cell size, because the contribution of the small scales to keep the turbulence alive on the large cells, large computation cells, is this backscattering energy is brought in by the stochastic model, and that's very new work actually. We call that forced eddy simulation because we force the unresolved eddies in with this model. Okay, that's the sources, and I would like to look a little bit on source breakdowns on all these various sources on aircraft. I took I wouldn't say I stole, but I took some information from a workshop in La Rochelle last year from Airbus. They presented, I think, a very, very interesting keynote lecture there. And they presented a source breakdown for aircraft in approach conditions. So this is really new data from Airbus 2015 from that workshop. And they didn't look at the like you see in most presentations, the situation for an aircraft, and the generation of those aircraft flying produced in the year 2000 or so. But this is a new aircraft, really modern tube and wing aircraft with a high bypass ratio engine already installed. So it's not the old situation, but it's already low noise aircraft, if you like. And what they usually present is engine noise contributions and airframe noise contributions. This is a small to medium range aircraft. That's the breakdown as Airbus sees it. For these very modern engines, they see the main contributors to engine noise is fan forward and fan rearward, is radiation. And on the airframe side, you have main landing gears about as important as slats. So that's the classical source breakdown. I think this is not really important to show the situation correctly. And I tried to take this as a basis to extract installation contributions out of this. I think one should have three categories of noise sources on an aircraft. It's not only airframe and engine. I think it's also installation. It's an own category of noise source. For example, the main landing gear, which is shown as one contribution, it's two contributions. It's the contribution of the isolated main landing gear noise and, of course, the gear flap interaction, which I just showed. And based on our measurements and our in the wind tunnel and flyover measurements, we estimate those contributions in this range about a little bit higher than for example, flap noise. It's not negligible. Same is true. There are contributions of jet flap interaction. You cannot ignore and say this is just some jet noise. No, it's not jet noise. It's something different. And of course, especially fan rearward noise is also heavily influenced, especially at the noise radiated rearwards. The fan is strongly influenced by the wing and the high lifted wing. There's a strong reflection, of course. And it's I think not clever to look it in this combined way, but to look at the fan as a source which you would have on a test stand and fan installed to the aircraft. That's different. And there's also an installation effect there. You see, by the way, also that the clean wing as a source of noise is about 20 decibels below the total aircraft noise. You do not see the clean wing. Okay, that's a typical source breakdown. For a long-range aircraft, that looks a bit different, because for long-range aircraft, the landing gear contribution is much, much higher. And again, if you break down this source breakdown into the classical component and installation, you see also very strong contributions there. I come back to that a little later. Acoustic installation effects is my second chapter, so to speak. And it's clear you have some sources, and they get reflected on the body of the aircraft. So you basically have negative effects if you have a classical aircraft configuration. It's all reflected additionally to the ground. You don't want to have that. You may think of funny aircraft configurations like this, where you put the engines on top of the wing to benefit from the reflection effects towards the ground. So you can reverse this situation and use reflection rather than to suffer from it. But there's one, well, okay. And this is also recognized by the EU. If you look into this strategic paper of the EU Flight Path 2050, they want a noise reduction of 15 decibels per operation for an aircraft. This is huge. This is absolutely huge. I don't know whether one can ever reach this, but it's at least a very strong objective. And there's one clear statement also there. You cannot achieve this only with classical noise reduction technology. That will not be possible. You need to think of including somehow the effects, or exploiting the effect of installation positively to reduce the noise in such an amount. And now you can, again, as I said, you can think of funny aircraft configuration. The question is, are such concepts good, shielding concept, or are they bad? And how good are they? So you have to do computations. You cannot measure this, basically. You cannot build this aircraft and fly it. You have to compute it. And it's very hard to compute that. You need to make simplifications. What we do is we are using a fast multipole boundary element solver for basically for the convective wave equation, or say we take into account flow effects using a Taylor transformation. And then you can really compute amazing things, like for a full-scale aircraft, a 30-meter size, you can compute 10 kilohertz or so for the whole thing. And that's very nice. You can start the studies. We, for example, looked at the influence when you have a flap or have no flap, and assuming a source at this position. You see 120 meters below this aircraft, the footprint, so to speak. You see dark means low noise, bright means high noise. You see, for example, here the beginning of the shielding of the wing. You see here effects of the fuselage shielding, and you see also here the signature of this installed flap here. This is for frequency of 2.8 kilohertz for some reason. If you plot the attenuation again as a carpet plot below the aircraft, this is in meters, 120 meters below the aircraft. Here we compared three things. We had the clean aircraft without a flap, so you see basically some shielding due to the wing mainly. Here we installed the flap, as you see here, and you see the extra shielding footprint here of the flap. And for some reason I come to later, we reduced the gap size to see whether such details play a role or not. So we said we take the same flap, but we reduce the gap size basically to 0. And what you of course see is there's basically no effect of such details. But I come to back that later. It seems you have a very nice tool to look at shielding and variations. You can see separately what is the contribution of the flap for the shielding. You can subtract, for example, the clean situation from the flap situation, and you see a nice shielding footprint of the flap, and you can use that for design. So seems to be all very fine, but I would like to show maybe one more case. You can also look at real engine sources like modes exiting from the fan. But I don't want to go into those details, but make a warning here. There's a warning. The warning is, so we do certain simplifications to simulate such installation effects. The typical things in order to have fast enough simulation tools available is we use typically inviscid flow Low Mach number is the assumption. We also assume small flow gradients, otherwise we cannot use the Taylor transformation. So we assume slender geometries. Typically aircraft are slender geometries. And we typically neglect sometimes geometrical details smaller than a wavelength, for example. We can do that. The question is such an approach always safe? And I want to show you one example where it is not safe. It's not very academic. It's, I think, relatively realistic. If you have a situation like this here, you have an engine, rear-mounted engine, and the sound of this fan is shielded by by a high-lift wing. That's a case we computed in an EU project, former EU project called NACRE. And what we did is we had the task to compute the shielding of this high-lift system. And typically what you do in such case, low speed, you neglect the details of that geometry and replace the whole thing by a plate, say, with the same plan form. And use uniform flow. So with a plate, if you replace this airfoil with a plate, you get a nice shielding in the shadow area here of this angle. So you get a nice shadow zone below this wing, amounting to something like 20 decibels shielding, which is very nice for a certain frequency here. And you could also use, for the actual geometry, uniform flow, much more easy to compute. And you get about the same result here, shielding of about 20 decibels. Now, if you take the actual viscous flow on this airfoil, your shielding is not 20 decibels, but only 8. And that's quite a difference. So typically you would say viscous flow has no effect on such simple cases with low Mach number. And this is obviously not the case. We were a little puzzled about this and thought, is it just numerics or does it has physical reason? And again, this is a situation. And I have to remind you on a certain effect which you have in aeroacoustics, that's refraction. If you have a shear layer, let's see a shear layer here, a simple jump shear layer, and sound hitting this shear layer from right, so against the flow direction, you have always a reflected part and a transmitted part. And if you are below a certain angle of incidence, the total angle of total reflection, then the whole sound is reflected at the shear layer. So 100% of the sound power is reflected at the shear layer, and no sound is transmitted. And there's, of course, not a jump to zero here, but the sound decays exponentially to the other side of the shear layer. Evanescent waves, they call evanescent waves. They are not sound waves because they are not traveling with the speed of sound. They are okay. So we looked again at our problem with this strange shielding situation. For uniform flow, you see the RMS distribution of the sound. As you are used to see it, dP by the end, the pressure derivative at the surface has to be 0, so the maximum of RMS pressure has to be on the surface itself. While when you have viscous flow, this maximum gets lifted off the surface, so the actual reflection does not take place on the geometry, but on the shear layers above the geometry. And what that means is another detail here. We looked at the orientation of the local flow and the total angle of total reflection for this case, and we ended up finding that this was exactly the direction out of which the sound came. So we had total refraction over this gap, evanescent waves in the gap, and so the evanescent waves interacted with the gap, and we reduced this problem to a much simpler one, from this original one to just a plate with a slot. And this is what I want to show you. We have here our shear layer. That's the dashed line. That's the shear layer, jump shear layer. We let plane waves hit this shear layer from right above, and they are totally reflected. So we get a checkerboard pattern on the upper side, and you see the evanescent waves below here. This is where I now put a geometry here. And I would like to show you a small animation. Unfortunately, I lost these animation during the traveling, but maybe this is a poor man's version of it. So there's nothing special you may expect. You see, Aha, that was very short. Waves are coming in, reflected perfectly at this shear layer, and this geometry is not here. It's just where I will put it later on, and you see the evanescent waves below. Now, if I place this object, and now this object is placed below the flow. It's not in the flow. It's below the shear layer. Then clearly you see that sound is radiated now in the lower half plane, and it's quite interesting because if you think there is still the shear layer, and 100% of the sound power is reflected, and additionally we see now sound radiated in the lower part. The first question which you may raise is sound power generated in this shielding problem. I think I cannot give an answer to this question yet, but of course, when you look into the literature, physicists know all this already. They all know everything already. It's a little bit frustrating, but not in acoustics, say. And they know that. They call that frustrated total refraction. That's the technical term, frustrated total reflection. Or other people in quantum theory, they call that a tunnel effect. This is a tunnel effect. And I found a nice picture, which is an analogy to this in optics. Maybe if you have your vodka glass, you know, in your hand, and you can still see, then what you have typically, you have a total reflection of light in this inner surface. And I don't know whether you have ever wondered why you see your fingerprint on this glass. You should not be able to see it because there is a total reflection of the light in the inner glass wall, basically. So you should not be able to see this, and that's the same, exactly the same effect as I showed here. It's called a tunnel effect, where the evanescent waves of the electromagnetic waves of light are interacting with this part of the finger surface, so to speak. This, what you see here, is the variation of this pattern on the side where the total reflection in the sound occurs. So it's an analogy. Again, the physicists know it already. And this is also a proof that it really is a relevant case. This is a simplified case where you have only a plate with a slot, plane waves entering, and this is the sound level which you get generated in this, or transmitted through this slot. In the case with a shear layer and with uniform flow without shear layer, you see really an extra effect, which is bad because it destroys your nice shielding effect of your wing. So beyond the critical angle of reflection, sound is not reflected at the surface but at the shear layer. Below the shear layer there are evanescent waves which are non-acoustic. When these non-acoustic waves interact with edges, they get transformed into sound again, and the tunneling basically is the pressure is sound, non-sound, sound again. So it's a change called tunnel effect. So that deteriorates our problem. And the point I wanted to make is, if you use simplified models for assessing the shielding properties of an aircraft, that may be very critical to neglect viscosity. This again is a problem, because if you have to resolve all the boundary layers on your shielding surface on a 30 meters aircraft, that's a computational problem. Okay, one more thing related to installation is, I think it's a very, very interesting concept for shielding, is buried engine intakes, which you know, of course, from military aircraft, but for civil aircraft could be interesting. We looked at this case several years back, but I wanted to show again that what you see here again is that due to the boundary layer on that plate into which this engine intake is buried, you get a very strong refraction effect. All the sound is refracted away from the surface up into the sky. That's very good. This is so effective because the sound hits the boundary layer on a very, very shallow angle due to this installation. And although sound is generated extra due to boundary layer ingestion on the fan, I would think that this effect is overcompensated by this installation effect. Very interesting. I think a very interesting concept. Okay. I think now I'm wrong here. All right. Yeah. Okay. Sorry. I have to go back to this. Sort of lost. All right. Let's go back to the overall aircraft situation. Let's try to make a noise reduction exercise on now taking into the account that there are installation effects on a traditional aircraft concept with high bypass ratio engines already installed. So the situation Airbus described in their keynote lecture. What I did here is I applied some noise reduction technology, which I think is feasible. For example, you could develop new liners for fan forward noise, better liners. There are ideas on this by 3 decibels, for example. You could also reduce the same thing on fan rearward noise with better liners. And if you have better liners for the source, you have it also here in this case automatically for the interaction. The reflection. You could reuse main landing gear noise reduction technology on the isolated main landing gear. They have some effects. Something like 4 decibels seem to be realistic. The same you can do for landing gear noise. And you could replace, for example, loud sleds by so-called advanced Kruger devices. We have seen that you can have a broadband noise reduction of 4 dBs or so. And you can do side edge noise treatment and so. And then you arrive at a result. The result is the total aircraft noise reduction is about 2.5 decibels. That's not really motivating. You do so much stuff and you get 2.5 decibels. Oh, that's not very good. So the conventional way of reducing noise on components is very important, but it's insufficient. That's what I want to say. To arrive really at strong changes required by the EU. Okay, I'm come to the final. If you now took the liberty to change a little bit your aircraft, still a tube and wing aircraft, not blended wing body or the big changes. So, okay, it's a big change, but it's not terribly hard. You can get rid of all installation effects just by design. That's the first point. You have no gear flap interaction because you have a body landing gear where the wake will never interact with anything. You have jet flap interaction not anymore because there is no flap behind the jet. You have no fan rearward reflection at the wing because the fan is radiating freely out and is even benefiting from the presence of the fuselage as a shielding surface, for example. So you get, by definition, by design, already rid of certain installation sources, and then apply your noise reduction technology, and all of a sudden you have 5 dB noise reduction. So it is worthwhile looking at the combination of classical noise reduction on components and the configuration itself. So the combined view is really important, I think. So avoid by design is a good point. I will not go into the details of this. One can achieve even more for long-range aircraft, I believe. But I slowly come to my conclusions. What are the challenges of low-noise aircraft design? Again, aircraft noise reduction component work is very important, but insufficient. One can do low-noise aircraft design studies based on mixed fidelity tools, I would say. But when you end up with a certain design, you have an idea and you want to compute it and find some result. At the end, this is a big problem of all this new aircraft design thing. How do you validate this? Basically, this is not a scientific work when you cannot validate it. And so far, nobody can really validate whether such an aircraft concept is really, 4 or 5 decibels less noisy than the standard one. And I think there is a need for testing complete aircraft in a wind tunnel on the controlled conditions. Like Airbus demonstrated it in the Clean Sky project, where they had this craw-driven full aircraft in the LLF wind tunnel of D&W. This is exactly the thing you have to do. You can do sort of aircraft noise studies in the wind tunnel, and that's the only way to really validate that. What it means for real aircraft with turbofan engines, you need turbofan simulators and attach it to aircraft models in wind tunnels, in acoustic wind tunnels. Then you are faced with new problems. You have then very small scales because you have to have downscaled full aircraft in your wind tunnel. Then you have very high frequency. You can only measure inside the flow because due to the high frequencies you cannot really properly radiate your noise through the shear layers of an open wind tunnel. And you, by definition, measure in the geometric near field. That again means that the far field can only be computed. So you need a combination of experiments and computation. And at the very end, I think you can only, at the end, you can only judge for validation your design with high fidelity methods. That's a big task and a large challenge, but it's there. I will skip this. It's relating to low impact noise. But come to my conclusions. Again, low noise component work is still very important, but insufficient. I was focusing on the importance of installation effects on aircraft. If you want to have a low noise aircraft, it's not enough to reduce the noise on the various components. That's what I wanted to say. We have strong effects source-wise and radiation-wise on aircraft. We have new challenges on experimental as well as on the numerical side when you look at installation sources and installation radiation effects, because very simply spoken, you have more than one component, and if you have more than one component in aerodynamic interference, you need large domains, either in the computations or in your test setup. You need large domains. That's difficult. We need, I think, to do that properly and validate and make a science out of it, properly founded science. We need also the way to validate full aircraft low noise designs by having aeroacoustically similar turbofan simulators. That's another thing to be developed. We can certainly use mixed fidelity tools to do the design of low noise aircraft. We have to be, when we do that, for certain conditions, and they are not exotic. That's a rear mounted engine is not really exotic. We have sometimes strong viscous flow effects, which we have to be careful about. And at the end, we need a high fidelity prediction to validate these designs, because we can basically not all the time build a new aircraft model with all engines and so on, and we cannot build this aircraft and fly it. The only way to really say at the end, this aircraft is so and so many decibels more silent than the other one, is to do a full-scale high-fidelity simulation. Though there is a new challenge for high-performance computing, I think. And the other one I didn't touch upon, but I think it's also important to find psychoacoustic measures. What is really annoying for the people, and we need useful psychoacoustic metrics, which we can use and turn into design requirements on aircraft. That's something which is, I would say, completely missing at the moment. But I think that it's very much needed. And I think that's about all I want to say. Thank you very much for your time. Thank you.
Thank you, Mr. Delfs.